Hello, everybody. In this video, we're going to be talking about rolling motion, angular momentum, conservation of angular momentum, and precession. Now, the first two questions are similar. The first question says, a sphere, a cylinder, and a hollow cylinder roll without slipping down an incline. Rank them in the order they reach the bottom. And to do that, we'll also do number two, so we'll do it simultaneously. It says, draw a free body diagram for the sphere from one, rolling without slipping down an incline. Which of the forces contribute to the net torque? And what is the net torque on the sphere? All right, so in either case, whether we have a sphere or a cylinder or any object with a radius that's rolling without slipping down an incline, we have something like this. So it has radius r, let's say it has mass m. If we draw a free body diagram, there are three forces on the object. There's the normal force, which points perpendicular to the incline, as the normal force always does. We have gravity, so it points straight down, and it starts from the center of mass of our object here. And then we also have friction. So friction occurs where the object meets the incline, and it always opposes motion. So it'll go in the opposite direction that it would roll down. And because it rolls without slipping, we have static friction. So it rolls without slipping, which means that this part at the bottom that actually touches the incline, is it moving with respect to our incline here? And so it's static friction. Okay, now the axis about which it rotates is an axis that goes through the center of mass here, which means that our weight produces no torque because it starts there. So the distance from the axis of rotation is 0. And also the normal force produces no torque because the angle between it and the vector that points from the axis of rotation to where the force is 180 degrees. Sine of 180 is 0. So the only force that actually produces a torque is our force of static friction. Okay. Now we can use energy to figure out which one will reach the bottom fastest. So with any energy problem, the first thing we have to ask is, what is the non-conservative work done? Well, we have two non-conservative forces here. We have the normal force and we have static friction. Now, the normal force can never do any work. And in this case, our force of static friction also doesn't do any work, because for friction to do work, it needs to slide against it, because the force needs to be active as the object is moving. And that just cannot happen with static friction. So static friction can never do any work. So altogether, our non-conservative work is 0, which means that we can use our energy equation, which says that our initial kinetic energy plus our initial potential energy, call that U, has to equal our final kinetic energy plus our final potential energy. Now, this is slightly different than an object sliding down an incline, because the kinetic energy is not just the linear kinetic energy, but there's also some kinetic energy due to the rolling. Okay. Now, if we have this object that's put at the top of the incline and released from rest, well, initially it's not rolling and the center of mass isn't translating. So our initial kinetic energy is 0. So we only have potential energy initially. Let's say that this thing is a height h. So we'll call the bottom of our incline here y equals 0. And the top is y equals h. Then our initial potential energy is just our mass times our acceleration due to gravity times h. Now, really, we should measure to the top or to the center of mass of our object here. So we could add plus r to our h here, but then when it gets to the bottom, it'll be at a height of r. So those parts just subtract away. So now at the bottom of our incline, we're at what we called y equals 0. So our final potential energy is 0, and we only have kinetic energy. So there's some energy due to the translation of the center of mass, which is the usual kinetic energy term that we know. And there's also some energy due to the rolling motion, which has this form. It's 1/2 times the moment of inertia times the angular velocity squared. Now, because our object is rolling without slipping, that means a point on the outside has gone the same distance in the same amount of time as the center of mass. So the distance our center of mass has traveled is the same distance that a point on the outside has traveled. And we know that is the radius of our object times the angular displacement. Okay. Now, if we differentiate this, we can see that our r is a constant. So the only part that we have to differentiate on this side is our theta. So the velocity of our center of mass is the same as our radius times our angular velocity. Now, the velocity of our center of mass is the same velocity that we have in our translational kinetic energy term. So we can replace our omega here with, if we solve for this, omega is v over r, which means we can rewrite our equation here. Like this. So now we only have one unknown, and that is the velocity. Before we solve for that, we need to know our moment of inertia. Now we want to make this general, so we're not doing it for any shape in particular, just a shape that has a radius. So all objects with the radius, so it's a sphere, a cylinder, a double cone, anything, has a moment of inertia that's some number times the mass times the radius squared. Now for a sphere, this number is 2/5. For a cylinder, it's 1/2. For a hollow cylinder, it's 1. But it's some number times this. So if we plug this into our equation here, so we have our 1/2 mv squared, and now we have a 1/2 mv squared, but it's multiplied by our number c here. Our r's canceled out, so it actually does not even matter the radius of our object. Now notice every term here has a mass in it, so the mass also doesn't matter. So we're left with something like this. We can factor our v's out here. So we have, or we got factor out a 1/2 v. So we're left with this. And so we can solve our velocity here, our velocity at the bottom as plus or minus depending on the direction. So our equation looks like this. This tells us the velocity at the bottom of our incline here. So notice if our c was 0 here, in other words, if our object had no moment of inertia, then we would have just gotten square root of 2gh, which is the same velocity for an object that just slides down an incline. So it moves slightly slower because we have this c here. And that's because some of the potential energy has gone not only into translating the mass, but also causing the rotation. Okay. Now, because when you roll down an incline, you move at a constant acceleration, whichever shape has the largest velocity at the bottom also got to the bottom the fastest. So we can try all of our different c values and figure out which object got to the fastest. Okay, I just looked them up to make sure. And the sphere has this coefficient in front of the moment of inertia of 2/5. A cylinder, a solid cylinder, has this coefficient of 1/2, and a hollow cylinder has a coefficient of 1. Now, because our term here is in the bottom, the bigger the c is, the smaller our velocity is, which means the slower that it took it to get to the bottom of the incline. So if we rank these, we want to rank them from smallest c to largest c. So a sphere will win if you put a race between all of these because it has the smallest c. Next, a solid cylinder. It'll make it to the bottom second. And then finally, a hollow cylinder will make it to the bottom last. Okay, so this is how rolling motion works. This is how you can figure out which object makes it to the bottom the fastest. Okay, so on to our next problem, which is problem number 3, which says use energy methods to determine the linear and angular speed of a sphere once it reaches the bottom of an incline of height 2.5 meters, and the sphere has a radius of 3.5 centimeters. Okay, so this is essentially the same thing here. Since we want a sphere, we'll use our c value of 2/5. So our velocity at the bottom is plus or minus depending on your coordinate system. Just use our number 2/5 here. And Yeah, it only asks for speed, so we can take the absolute value of this. So it's just a square root of 2gh over 1 plus 2/5. You could simplify this or not, it doesn't really matter. And we also want to know the angular speed. So like we saw before, angular speed and velocity are related like this for an object that's rolling without slipping. And so we can find our angular velocity by dividing our regular velocity by r. So in this case, our omega is still plus or minus from the velocity. So this is our angular velocity. We only wanted speed, so we can drop the plus or minus. So our angular speed is this, while our linear speed was this. Okay, so easy enough. The next question says, a car travels at 60 miles per hour for 30 minutes, and the wheels of the radius of 1 foot roll without slipping the entire time. What distance has a point on the outside of one of the tires rolled through? What was the angular speed of the point on the outside of the tire during the trip? And what were the centripetal and tangential accelerations of a point on the outside of the tire? So this is another rolling without slipping problem. So first off, it says the car travels at 60 miles per hour for 30 minutes. So it's at a constant velocity. We know how to find the distance that it traveled is just our velocity times time. So this is our 60 miles per hour. We need to multiply by time, but it needs to be in the same units. So 30 minutes is half of an hour, which means that the car has traveled 30 miles. And because the tires are rolling without slipping, then a point on the outside of the tire has taken the same distance or traveled the same distance as the center of mass. So a point on the outside of the tire has also traveled 30 miles. Now we want to know the angular speed. Well, we know that for slipping or rolling without slipping, the velocity of our center of mass is our radius times our angular velocity, which means that our angular velocity is our velocity, which we said was 60 miles per hour, divided by our radius. And our radius was 1 foot. So we need to get these in the same units. In 1 foot, or in one mile, there's 5,280 feet, which means that our angular velocity is what? Is 316,800 radians per hour. And we can just keep it in this unit, that's fine, because that's the units that we were given it in. And we also want to know what is the centripetal and tangential accelerations of the outside of the tire. Well, let's do the tangential acceleration first. The tangential acceleration is our radius times our angular acceleration, but we have a constant angular velocity. That means our angular acceleration is 0. So our tangential acceleration is also 0. Now, the centripetal acceleration is slightly more complicated. We know the centripetal acceleration of an object that's moving in a circle, just like a point on the outside of the tire, is our velocity squared divided by our radius. Or if we use this, it's our radius times our angular velocity squared. So our radius was 1 foot. Our angular velocity was this thing. And we should probably convert those feet to miles. So in 1 mile, there's 5,280 feet, which means that our centripetal acceleration is what? It's 1.9 times 10 to the 7 meters per second squared, or not meters, sorry, miles per hour squared, okay? All right, our next question says, why does precession occur? So first off, what is precession? Precession is when an object, so for instance, a top, this is a poorly drawn top, it's rotating about some axis, and the axis about which it's rotating is rotating. So it's like if a top is spinning like this while that angle rotates. And the reason why this happens is because our net torque is equal to the time derivative of our angular momentum. So here our angular momentum is in this direction, but we have a torque in a different direction. So we have a center of mass somewhere, which means that we have a weight somewhere as well. So if we call this point our origin, then we have a torque that goes this way. It goes into the page. Now, if torque is along our angular momentum, then whenever it changes it, that's just going to change the rate at which it rotates. So it could either make it rotate faster or make it rotate slower. But if torque is along a different axis than our angular momentum, then it's going to change its angular momentum in that direction. So in this case, it wants to change the angular momentum in this direction, which means we have to add a second axis of rotation, and that's why we get precession. That's why we get something like this. Okay, our next problem says Lois Lane watches Superman, who is 80 kilograms, this is number 6, fly at a velocity of 10 meters per second in the x direction. And when she initially sees him, she estimates him to be at a position of 10 meters in the x direction, minus 40 meters in the y direction, and 20 meters in the z direction. We want to know Superman's angular momentum relative to Lois. We know our angular momentum as a vector is given by r cross p. So we need to find the momentum and we need to find our position. Now this is our position at one time. So we need to find a more general formula for the position at any time. So our velocity is constant and it's in the x direction, which means that our x part is our 10 meters, which we were initially, plus our 10 meters per second times time. That's in the x direction. And we have the rest of these stay the same, minus 40 meters in the y direction, plus 20 meters in the z direction. Okay, now we need to cross this in to our momentum. We know our momentum is our mass times our velocity. So for Superman, that's his 80 kilograms. Said his velocity was only in the x direction, which means that our momentum is 800 kilogram meters per second in the x direction. So we need to take the cross product between these two things. So we know how to take a cross product. We draw a 3x3 matrix. The first column has our unit vectors in the x, y, and z direction. Our second column has our first vector. So rather than write all these out, I'll just write Rx, Ry, and Rz. And our third column has our third vector, our second vector. The second vector only has a component in the x direction. So I'll put Px. Okay, now to actually take a cross product, we take the determinant of this matrix. So for x, for the first component, we start with I hat and we go diagonally. So first we go diagonally to the right, and that gives us a positive sign, but it's 0. Then we go to the left, and that gives us a negative sign, but it's 0 as well. We could do the same for y. We go diagonally, and because we went right, it's positive. So we have this RZPX, and then we go the other direction with a negative sign, but it's 0. So our y part is just this. Now we can do the z. So we go diagonally. We got 0. We go the other way. we get something that's not zero. Because we went left, it's negative. Okay. So this is our angular momentum. So our L then is the Z part of our direction, which was 20 meters, times our momentum in the X direction. So we have 16,000 kilogram meters squared per second in the Y direction. And then we have the Y part of our position vector, which is minus 40. So the minus here can cancel the minus here. And we have 40 times 800, which is 32,000 kilograms meters squared per second. And that's in the Z direction. So this is Superman's angular momentum with respect to Lois. Now we want to know what the torque on Superman is relative to Lois. So we know that torque, at least net torque, is our time derivative of our angular momentum. This thing does not change with time, right? There's no t's in here. So this is just zero. Okay. Now in the next problem, Superman is in a different position and now he's accelerating. So his new position is 300 meters in the X direction, and the Y and Z directions remain the same. This is number 7. And he's accelerating an acceleration of 15 meters per second squared in the X direction. And now we want to know Superman's angular momentum again, and also the torque on it. So we need to write his position as a function of time. Now, when he started accelerating, he still had his same velocity that he had in the last problem. So last problem, he had a velocity of 10 meters per second in the X direction. So we still have this term, but now he's also accelerating. So to find that, we know that our kinematic equation says that our X at any time is how we started, plus our initial velocity times time, plus 1/2 our acceleration times time squared. So we'll do this here. This is what we did to get this term. For the acceleration term, we need to divide by 2. So 15 over 2 is 7.5. And then we need to multiply by t squared. So all this is in the X direction. And then our Y and Z parts are the same. Okay. And now we need Superman's momentum because we're looking for his angular momentum, which is his position crossed with his momentum. Well, Superman's momentum is his mass times his velocity. Now here, velocity is not just a number, it's a function of time, right? Because he's accelerating. So we know that from our kinematic equations, velocity is initial velocity plus acceleration times time. Superman's mass is still 80 kilograms, but now his velocity is that initial velocity of 10 meters per second plus the acceleration times time. And this is all in the X direction. So if we work that out, we have 800 kilogram meters per second plus 1,200 kilogram meters per second squared times time in the X direction. So once again, we need to take the cross product between these things. So we draw a 3x3 matrix. Our first column is our unit vectors. Second column is our first vector. So I'll just write Rx, Ry, and Rz. Now our third column is our third vector, which only has an X. We take the cross product the way we usually do. That gets us 0. That gets us 0. That gets us a number. So we have Rz times Px that gets us 0. So this is the whole y part. Our z part gets 0. And we went left, so it's negative. So minus ry px in the z direction. This is the same form that we got before, right? Because our vectors here had the same form. Our position had an x, y, and z part, and our momentum only had an x part. So we get the same looking form here. So the z component of our position is minus 40 meters. We have to multiply that with px. Now our px is all of our p, is this 800 kilogram meters per second plus 1200 kilogram meters per second squared times time. So this is the y part of our angular momentum. Then we have to subtract the y part of our position, which is minus 40. So the minuses go away and I'll have positive 40. Did I do this wrong? Oh, I did this part wrong. No, yeah, I did this part wrong. I was supposed to do the z part of the position, but I did the y part. The z part was 20 meters. But here we have 40 meters times the x part of our momentum, which is our whole momentum. And that's in the z direction. So what are we left with? We have 16,000 kilogram meters squared per second plus 24,000 kilogram meters squared per second squared times time in the y direction. So this is our full angular momentum. And for the z part, we have 32,000 kilogram meters squared per second plus 48,000 kilogram meters squared per second squared times time. So this is Superman's angular momentum. And now we also want to know his torque. Well, we know that torque is the derivative of our angular momentum with respect to time. Well, this is independent of time, but this isn't. So his torque is 24,000 Newton meters in the y direction plus 48,000 Newton meters in the z direction. Okay, so because his angular momentum was a function of time this time, he did have a net torque on. All right, our next problem says that an ice skater is spinning with her arms outstretched. What happens to her angular velocity when she pulls her arms in? So we can treat an ice skater like an isolated system. It's not really, because there is friction between the skates and the ice, but we'll assume that it's approximately, that the friction is approximately negligible. So in that case, in an isolated system, angular momentum is conserved. The angular momentum before some interaction, something happens, is the same as the angular momentum after. So if an ice skater is spinning with her arms outstretched and then she brings them in, the angular momentum in both of these cases have to be the same. And for a rigid body, angular momentum is equal to the moment of inertia times the angular velocity. So we know that that moment of inertia is this weird integral for a rigid body, but essentially it depends on how much mass is far away from the moment of inertia. Now with her arms outstretched, she has lots of mass that's far away from the axis of rotation, which means that she has a really big moment of inertia. Now, when she pulls her arms in, she takes mass away from the axis of rotation, which means that she decreases her moment of inertia. And for angular momentum to remain the same, that means her angular velocity has to increase. So when she pulls her arms in, she starts spinning faster. All right, so that was number 8. Number 9 says, true or false, an object with an external force on it can have no angular momentum. An object with an external force on it can have no angular momentum. That is true. So if we have some object that has a force on it, we could just be accelerating the center of mass rather than giving it an angular momentum. So just to expand on that a little bit, our angular momentum is our position crossed into our momentum. And so this is a coordinate system dependent thing. It depends on where you set your origin, what this is. It also depends on how the coordinate system is moving to find the momentum. But you could have a coordinate system where your origin is here, and now your r vector and your p vector are parallel, which means that the angular momentum is 0. All right, so number 10 says true or false, an isolated system has a constant angular momentum. That is true. As long as you're in an isolated system, the angular momentum is conserved, which means that it can't change, which is the same as linear momentum. So number 11 says 2 spheres of mass 2.5 kilograms and radius 10 centimeter are attached to a 1 meter rod of mass 0.5 kilograms. And the whole apparatus is rotating about its center of mass with an angular velocity of 15 radians per second. What is the object's angular momentum? All right, so we have something like this. This distance is 10 centimeters, the radius of our object, and our rod is 1 meter long, and it's rotating about the center of mass. Okay, so to find the angular momentum, we have a rigid body here, so it's equal to our moment of inertia times our angular velocity. So we need to find the angular momentum of this thing, or the moment of inertia rather of this thing. So the moment of inertia of an object with multiple objects in it is just the sum. So we have the moment of inertia of our rod rotating about its center of mass, plus the moment of inertia of each sphere, rotating about an axis that's not through its center. So let's find the spheres first. We know the moment of inertia of a sphere about its center of mass is 2/5 mr squared. M is its mass and r is its radius. But we're not rotating about the center of mass. We're rotating about this point, which is 1.1 meters away, right? It's 1 meter, or sorry, it's 0.6 meters away. It's 0.5 meters from the edge of the sphere to the middle of the rod, and then 10 more centimeters to the center of mass of our object. So the moment of inertia of our sphere by parallel axis theorem is the moment of inertia about the center of mass plus the mass times the distance to the new axis of rotation squared. So this is our 2/5 mr squared plus our mass times half of the length of our rod plus the radius squared. So with our numbers, that is what? So the moment of inertia of each sphere is 0.91 kilogram meter squared. And we have 2 of them. So now we need the moment of inertia of the rod. So the moment of inertia of a rod rotating through an axis through its center is 1/12 its mass times its length squared. So for our numbers, this is 0.042 kilogram meter squared. So our total moment of inertia then is twice the moment of inertia of our sphere, because we had two spheres, plus the moment of inertia of our rod, which is 1.86 kilogram meters squared. Now our angular momentum is this moment of inertia times our angular velocity. Our angular velocity was given in the problem as 15 radians per second, which means that our angular momentum is 27.9 kilogram meters squared per second. Okay, now our next problem, number 12, said that we have internal forces on the same object from 11, which relocate the spheres from the ends of the rod to 25 centimeters away from the center of mass on each side. What is the new angular velocity? So we had our object that looks like this. Somehow we have internal forces. So the fact that they're internal is actually important, because as long as there are no external forces, that means that our angular momentum is conserved. So these internal forces bring our spheres in. So now they're somewhere like this, but our angular momentum is constant, which means that our angular velocity is going to have to increase because we've brought our mass closer to the axis of rotation, which means that our moment of inertia has decreased. So first, let's find the moment of inertia of this thing. So let's see. It says that the spheres relocate from the ends of the rod to 25 centimeters away from the center of mass. So I take that to mean that from the edge of the sphere, this is 25 centimeters or 0.25 meters. So our moment of inertia then is still the moment of inertia of our rod plus the moment of inertia of our spheres. Now the only thing that's changed about the spheres is how far they are away from this parallel axis to the axis through their centers of mass. So we still have this center of mass moment of inertia plus our md squared here. But now our d, instead of being the half a meter plus the radius, is 0.25 meters plus the radius. So that's 0.35 meters. And so our total moment of inertia for each sphere is 2/5 times our mass. What was our mass? 2.5 kilograms times our radius, which is 0.1 meter, plus our mass again, times our 0.35 meters squared. So the moment of inertia of each sphere is 0.316 kilogram meter squared. Now notice this is much less than what we had before. Before we had 0.91, so it's decreased by a factor of almost 3. That's because we brought them in so far. Most of the moment of inertia came from this term, and because it was so large in the last problem. But here they've come in some, so we have a smaller one. So our total moment of inertia is the moment of inertia of our rod plus twice the moment of inertia of our sphere, because we have two spheres. So this is what? Our total moment of inertia is 0.673 kilogram meters squared. So our angular momenta has to be the same as it was before. The last problem we calculated to be 27.9, which means this has to be equal to our moment of inertia here that we just calculated, times our new angular velocity. So if we divide by our moment of inertia, we find that our new angular velocity is 41.5 radians per second. And as we said at the beginning, it has increased significantly from the 15 radians per second that we had before. All right, we have one more problem for our short answer, and then we'll look at the long answer. What type of friction affects objects rolling without slipping? So we talked about this before. If you have an object that's rolling without slipping, that means this point at the bottom where it's in contact with the incline, or it could be flat, it doesn't matter. Isn't moving with respect to it, which means for rolling without slipping, we have static friction. And for rolling with slipping, then there's some slipping, which means that this point that's in contact with our surface here is moving. And so we have kinetic friction for slipping. And in which case does friction do work? Static friction can never do work, because for friction to do work, you need sliding, which means you have to be moving with respect to the surface. So only in the slipping case do we have work. Okay, long answer problems. First question says that we have a merry-go-round of radius 2.5 meters, and it has a mass of 1,200 kilograms. And there are 5 children that have a mass of 25 kilograms, and they're initially located at 1.25 meters from the center. And it has an angular velocity of 12 radians per second. If all the children move to the outside of the merry-go-round, what will the new angular velocity be? So this is another conservation of angular momentum problem. So our momentum before the children move out to the outside has to be the same after they do. This is a rigid object, which means that we can write our moment of inertias as we can write our angular momentum rather as our moment of inertia times our angular velocity. When the children move to the outside, they're changing the moment of inertia. So by changing it, the angular velocity has to change as well. All right, so let's calculate the initial moment of inertia. So we have our merry-go-round here, which is like a disc. It has a radius of 2.5 meters, and we have 5 children. It doesn't really matter where they are around the disc, but they're all located halfway between the center and the outside. So they're all at 1.25 meters. So our moment of inertia then is the moment of inertia of our disc or our cylinder plus the moment of inertia of these children. So we'll treat them as point masses, and point masses have a moment of inertia that is their mass times their distance from the axis of rotation squared. And there's 5 of them, so we'll just multiply this by 5. Okay. Now the moment of inertia of a solid disk is 1/2 its mass, which we said was 1,200 kilograms, times its radius squared, so that we add each child is 25 kilograms. They're located at 1.25 meters. That's squared. So our initial moment of inertia is 3,945 kilogram meters squared. Now, in our next iteration, once the children move to the outside, everything is the same, except for now the children are a distance of the radius, right? So they all move from our 1.25 meters all the way to the outside at 2.5 meters. So our new moment of inertia is the same thing, except for this 1.25 is now 2.5. So our moment of inertia there is 4,531 kilogram meters squared. This is our final. So our initial angular momentum is our initial moment of inertia times our angular velocity. The problem says that our initial angular velocity is 12 radians per second. This has to be equal to our final moment of inertia times our final angular velocity. So if we calculate that, it is 10.4 radians per second. So this makes sense. As the children move to the outside, the moment of inertia increases. So to compensate, the angular velocity has to decrease. All right, so the next part is, what can the children do to maximize the angular velocity of the merry-go-round? And what will its angular velocity be then? Well, the children can do one of two things. Either they can jump off of it completely, then their mass doesn't contribute to the moment of inertia at all, or they can all crowd around the center. So if they could all stand on each other's shoulders or whatever at the very center, then they're not rotating, right? They're at the axis of rotation. So their distance here is 0. So in either case, what they can do is make the total moment of inertia only due to the disk itself and not due to them. So in that case, our moment of inertia would be just the moment of inertia of the disk. Which is 3,750. So we can do the same thing we did before then. Our angular momentum before the kids have moved to the center, which was this. Has to be equal to our angular momentum now, which is our moment of inertia that we just calculated, times our angular velocity. So our angular velocity then would be 12.6 radians per second. So the vast majority of the moment of inertia was from the disk, but if the kids wanted to go as fast as possible, they could limit their moment of inertia either by jumping off or by moving to the very center. And then the angular velocity would be 12.6 radians per second. Okay, our last long answer problem says that the merry-go-round from the last problem with no children on it, so this is, has a radius of 2.5 meters. It has a mass of 1,200 kilograms. Is rotating at 12 radians per second clockwise. And a child that runs and has a velocity of 10 meters per second towards the far right side of the merry-go-round. The child jumps onto the far edge, and the two then rotate together as a single body. What is the angular velocity of the merry-go-round child combo? And how fast would the child have to run along the same trajectory to make the merry-go-round actually stop? Okay, so we have our disk here, which is rotating clockwise. So that's this way. And we have a kid that's running toward the far right end. So we have our kid that's running this way. This once again is a conservation of angular momentum problem. So our disk has some angular momentum about an axis through its center here, but the kid also has some angular momentum here. Now, if we do the right-hand rule, we can figure out the direction of the angular momentum. So for our rotating cylinder here, if we curl our fingers in the direction of the rotation, our thumb points in the direction. So here, if we curl our fingers around, our thumb points into the page. So the angular momentum of the disc is along the negative z direction, if we use a regular coordinate system. And for the kid, he has a position that looks like this. His momentum is in the same direction as his velocity. And so if we do the right-hand rule, then his momentum is in the positive, or his angular momentum is in the positive z direction. So since these are along the same axis, this is a one-dimensional problem, and we don't have to worry about our vector stuff. We'll just call the angular momentum of our disk negative, and this kid's angular momentum positive. Okay. So let's first find the angular momentum of the disk. Well, the disk is a solid object, so it has an angular momentum of its moment of inertia times its angular velocity. So we just calculated this. This is half its mass times its radius squared. And the problem says that our angular velocity is 12 radians per second. So the angular momentum of our disk is 45,000 kilogram meter squared per second. All right, now let's find the angular momentum of our kid. Well, we know that our angular momentum is our distance times our momentum times sine of the angle. We said this was negative, by the way. Okay, and another way of saying this is that it's the lever arm times the momentum. So remember, the lever arm is the part of the distance that's perpendicular to the momentum. All right, so our momentum is this way. It's in the y direction. And so the only part of the position that we care about is the part that's perpendicular to the y direction. So in other words, the part that's in the x direction. So the only thing that matters is this distance. Since he's going to the far edge of the sphere, this distance is the radius of our sphere. So our angular momentum of our kid is the radius of our sphere times his mass times his velocity. So it says the kid is running what? At 10 meters per second. He has a mass of 25, and we know our radius. So he has a momentum, an angular momentum of 625 kilogram meters squared per second. And we said it was positive because that's what the right-hand rule tells us, right? We stick our fingers in the direction of our r vector. We curl it in the direction of our momentum, and our thumb points up. So it's in the positive z direction. Now, our total initial angular momentum is the angular momentum of the disk plus the angular momentum of the kid. So before the kid jumps on, let's call this L, the kid. This is our angular momentum, and it has to be equal to the angular momentum after he jumps on. So let's try to figure out what that is. So he jumps on. Now we can treat him as a point mass that's at the radius. So our final angular momentum is that moment of inertia times our new angular velocity, which is what we're trying to find. So our moment of inertia is the moment of inertia of the disk plus the moment of inertia of our point mass, which is our kid who's located at the radius. So if we calculate that, it's (3,906) kilogram meters squared. Okay, so now we can put everything together. So the momentum, the angular momentum of our disk which is this negative 45,000, plus the angular minimum of our kid, which is 625. So that's minus 44,375 has to equal the moment of inertia of our kid plus disk combo times its new angular velocity. So we can solve for that, and it's what? Minus 11.4 radians per second. In other words, 11.4 radians per second clockwise. So initially the disk was going at 12 radians per second clockwise. This kid jumped on it because of the way that he was running. It slowed it down by 0.6 radians per second. Now the next part of the problem says, how fast would the kid going along the same trajectory have to go to make the merry-go-round stop? So in other words, we want this final velocity to be 0. And so we want the moment of inertia of our disk plus the moment of inertia, or sorry, the angular minimum of our disk plus the angular minimum of our kid add to be 0. So we found that the angular minimum of our disk was minus 45,000. So we want the angular minimum of our kid to be positive 45,000. And we know that is equal to our radius, which is 2.5 meters. That's where he jumps, times his mass, which was 25 kilograms, times some velocity that we don't know. Some velocity that we don't know to make this work out. So if we divide our angular momentum by our radius and by the mass of our kid, we can find that his velocity would have to be 720 meters per second for him to have enough angular momentum such that when he actually jumps onto the disk, it stops. All right, so I'll see you guys in the next video.